Welcome to Chem 1A at Shasta College. This is a screencast on precipitation reactions and also an introduction to net ionic equations. If we mix together a solution of lead 2 nitrate and potassium iodide, and here's what it looks like both on a macroscopic level, both solutions are clear and colorless, and on an atomic level where the lead 2 nitrate consists of lead 2 plus ions and nitrate NO3 minus ions dissolved in water, and the potassium iodide solution is a mixture of potassium ions and iodide ions in solution. And when those are poured together, a thick, bright yellow solid material appears, and if we wait a little while, that material settles to the bottom of our beaker. So we form a solid yellow substance, which is in fact lead 2 iodide. And so what we have on an atomic level once the reaction has taken place is we still have some potassium ions and some nitrate ions floating around in solution, but then we have an ionic compound, lead 2 iodide, which consists of formula units of 1 lead 2 plus ion and 2 iodide I minus ions in a normal ionic compound type of array. So let's look at what's going on here. Well, lead 2 nitrate is PbNO3 aqueous solution. Potassium iodide is Ki, also aqueous solution. We mix them together and they form lead 2 iodide, PbI2, which is a solid, and potassium nitrate, KNO3, which is aqueous. Now, a couple things to note. One is this equation isn't balanced, and that should be not too hard to do. We have 2 Ki's and 2 KNO3s to make this balance. And then we also note that what we started with was lead associated with nitrate and potassium associated with iodide, and after the reaction is complete, the lead is associated with the iodide and the potassium is associated with the nitrate. So in other words, these two substances kind of switched partners. Let's take a look at this again on a molecular level. What ends up happening we just talked about, and this is what we call a precipitation reaction, and it occurs when we have 2 aqueous solutions that mix and a solid, an insoluble substance, which we call a precipitate, is formed, and this solid will precipitate or settle to the bottom of our container. This is one major type of chemical reaction that occurs. Now let's look at this in a little more detail on a molecular level. Here's the lead nitrate, lead 2 nitrate, and potassium iodide, schematically shown very simplistically. The lead nitrate consists of lead ions and nitrate ions. The potassium iodide consists of potassium and iodide ions. And when we mix these together, essentially what can happen is the lead 2 plus, which had been in solution with nitrate, can associate with the I minus because positive and negative attract. And then similarly, the K plus can attract to or associate with the NO3 minus instead of the I minus that it had been in solution with. And so we have a switch or swap of partners, at least potentially, and we potentially make PbI2 and KNO3. Now, in many cases, there's a potential partner swap between 2 aqueous solutions. We only have precipitation reaction if one of the new combination results in a solid. That doesn't always happen. So here's a little bit of a visualization with the right stoichiometry, PbNO3 and then 2 Ki's. Mix them together. Ions move around, bump into each other, new combinations can happen, and ions that attract strongly enough to be held together will do so, and what we get is PbI2 settling to the bottom of the container, and K plus and NO3 minus still floating around in solution. Now let's look at this reaction in a little more detail with something that chemists often do. First of all, the overall equation is sometimes called the molecular equation or the total reaction equation, and it shows everything that's involved in the reaction. Lead-2 nitrate and potassium iodide are the reactants. Lead iodide and potassium nitrate are the products. Shows the phases of everything. So this is a perfectly good description of what's going on. But what we sometimes do is we note that lead nitrate, lead-2 nitrate, is an aqueous solution, which means even though we're writing the lead and the nitrate as if we're writing them together, they're really not together in solution. The lead ions and the nitrate ions are actually floating around separate from each other. And the same thing applies to the potassium iodide. It's really not Ki stuck together, it's really K pluses and I minus floating around in solution. But then for the products, the lead iodide, lead-2 iodide, that actually is stuck together. The Pb and 2I minuses, Pb2 plus and 2I minuses actually do stick together, form a solid, and then the K plus and the NO3 minus, those are not stuck together. And this is what's called the overall ionic equation because it shows in great gory detail all the substances involved, and it shows whether they're actually stuck together, as in PbI2, or not, is in all the other substances. And what we note in an overall ionic equation for a precipitation reaction is that we have ions, in this case nitrate and potassium, that start as ions floating around in solution, aqueous, and end up as ions floating around in solution, aqueous. In other words, they don't really react or change. These we call spectator ions because they just spectate. They watch the reaction happen, but they don't actually participate in it. They are essential. We can't have a solution of just lead-2 plus ions. It has to have a negative ion to balance charge. We can't have a solution of just iodide ions. It has to have a positive ion to balance charge. So these ions are important, but since they don't participate in the reaction, we often just cross them out. And then we notice what happens is the heart of the reaction is that lead-2 plus ions combine with iodide ions, I minus, to make lead-2 iodide, PbI2 solid, and this is what we call the net ionic equation. And the net ionic equation is essentially the boiled down version of what actually happens. One thing you're going to need to be able to do is to write overall reaction equations, and then work your way through the ionic equation, the overall ionic equation, to a net ionic equation. The suggestion is you start by writing everything out in gory detail and cancel out as appropriate. But with a little practice, you probably can go right from the overall reaction equation, the molecular equation, right to the net ionic equation. Do that if you can get there. If you make mistakes, it's better to take the time to write everything out. Now, one other thing to note, we never really talked about how we knew that the solid, that yellow solid precipitate that formed, how we knew that was the lead-2 iodide rather than potassium nitrate. And we have something known as solubility rules that help us in this. There's all kinds of different versions of solubility rules. We'll refer to the one in the OpenStax chemistry textbook here, and it's essentially a listing based upon empirical evidence of soluble compounds and exceptions, and insoluble compounds or not soluble compounds and exceptions to that. Note these are solubility rules specifically for ionic compounds dissolved in water, and generally speaking, we'll just go through them kind of quickly. Cations of the alkali metals, lithium, sodium, etc., are soluble without exceptions. Ammonium ion in a compound is going to be soluble, no exceptions that we're going to note at least. Halides, so chloride, bromide, iodide, are mostly soluble. Most compounds containing these are soluble, but exceptions are things like halides of silver ion or mercury 1 ion or lead 2 ion. So normally we'd expect iodides to be soluble, but with lead they're not. So this tells us that lead 2 iodide would be a precipitate. But it also tells us that potassium iodide would not be a precipitate, and it tells us that compounds that contain nitrate, so potassium nitrate, our original substance, and lead nitrate, our original substance, and potassium nitrate are one of our ending substances. Neither of those are going to form precipitates. They're soluble. And then just also to note, this wasn't the example, but carbonates, chromates, phosphates, and things containing sulfide ion, those ionic compounds are generally insoluble, but there are some exceptions, and then same with hydroxide. So one thing you're going to want to be able to do is predict formation of precipitates, and you will have access to solubility rules to be able to do that. So that's it for the introduction to precipitation reactions and net ionic equations.